Okay. Hi, everybody. So, actually, we will continue our studies about matrices, and we were talking about subspaces, basis, dimension, and rank. And today we'll talk about dimension and rank. So, we have observed that although a subspace will have different bases, each basis has the same number of vectors. This fundamental fact will be of very important or vital importance from here on in this book. And we are just actually, what we have learned so far, we are actually going to attach some special names. And as we have observed in the previous examples, that a subspace may have different bases. That means that the bases may contain different vectors. But what we have observed that actually each basis have or has the same number of vectors. Actually, this is a fact. In general, it is true. So we are going to give this as a theorem and prove it here. So now the basis theorem says that let S be a subspace of R sub Rn. And actually it is a subspace in n-dimensional space. Then any two bases for S have the same number of vectors. So actually if we are talking about, let's say here we are talking about this our n-dimensional space, and we are talking about some subspace here. When I actually say subspace, you know that we immediately had to think of those three properties, and assume that in two different ways. Actually, we have two bases, two different bases, and those bases have different number of vectors or basis vectors. So suppose now here we have two bases. The first one actually it has R vectors, U1, U2, UR. And again, when we just say basis, we know that it spans this subspace S, right? And also this U1, U2, UR, these vectors are linearly independent. That is the definition of basis. And also this is another basis, V1, V2, Vs, and we are going to show that actually this R and this S, they must be equal to each other. Okay, so we are going to show this. How we are going to show this here? I will show that actually when we say that they are equal, in some different ways we can show this, but here I will show that R cannot be equal to less than S, or R cannot be greater than S. Okay, this is not possible. So this forces that this R then must be equal to S. Okay, if you're talking about two different real numbers, let's say you just pick any two real numbers. If I know that actually this R is not less than S, and also if I know that R is not greater than S, that means that I can draw a conclusion that this R must be equal to S. So it'll just show in this way. Now I'll just consider the first case and also the second one when R is greater than S. In similar way, it can be proved, and we just interchange the role of that's B and C. That's all. So now suppose that R is less than S. So we are talking about two bases here, and I'm assuming that this B contains a less number of vectors than this C. Okay, that means that here we have less. Maybe here we have, let's say, two vectors. Here, maybe here we have three vectors or four vectors. Now we will show that this is not possible. Okay, if we assume that R is less than S, and here, if you just pick any vector, right? Or is that, if you just write, for example, this C and the linear combination of these vectors, right? And since we know that this V1, V2, and Vc, and we are assuming that this is also a basis, that means that these vectors must be linearly independent. And if you just write the linear combination of this VV, V1, V2, Vs, the only way actually that makes this expression zero is the C1, C2, Cs, those, what is it? Coefficients must be equal to 0. Now we will see that actually we will now I'm going to show that actually also it has some non-trivial solution that is actually how to say that's brings us a contradiction, because here we are assuming that actual C is a basis. That means that V1, V2, Vs, these vectors are linearly independent, and that linearly independent means the only real numbers, right? The C1, C2, Cs that takes these vectors, linear combination of these vectors to zero is zero, right? The C1, C2, Cs, zero. But now I'll show that actually this is a wrong guess. Now, since, and also B is the basis for S, C is the basis for S, that means that if you just pick any vector from S, right, we can write it as a linear combination of these basis vectors. In particular, for example, here, if you just write V1, right, also this vectors V1, V2, Vs, they are living in S. And also this U1, U2, UR, also they are living in S. If you just pick any vector from S, I can write it as a linear combination, either these vectors, U1, U2, UR, or either these vectors, V1, V2, Vs. So in particular, if you just pick V1 from this S, I can write it as a linear combination of these basis vectors, because these vectors are basis vectors. So let's say this A1, 1U1. I'm just using here double subscript notation because I'm going to use this in every row. So it's just actually scalar here. U1 plus A1 to U2 plus A1R UR, because here we have R vectors. If you just pick any vector from S, in particular this V1, I can write it as a linear combination of these vectors. And also V2, for example, also we can write it as a linear combination of these vectors, U1, U2, UR, and dot, dot, dot. And also if you just pick the last vector here, VS, and also I can write it as a linear combination of these vectors, U1, U2, UR. Okay, so now if you just substitutes these values, this V1, V2, Vt, into the first equation. So V1 equals this. If you substitute here, what we have here, C1. Here we have C1 times the value of V1. V1 is this. So here we have A11 U1 plus A12 U2 plus dot, 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 A1R plus UR plus. So now here we have C2. So here we have C2 times, instead of this V2, I will write this expression and the linear combination of these factors. So here we have A21 U1 plus A22 U2 plus dot, 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 A2R UR plus, and this way we can continue this. And also for Vs, we can substitute this expression, that is AS1 U1 plus AS2 U2 plus dot, 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 ASR UR. That's equal to 0. So now I can regroup this. As you see here, it's a long expression. Here we have long expression. Now, as you see here, this U1, U1, U1 is a common vector, right? And all of these are the coefficients of U1 plus and U2, U2, U2. Also, it's like a common factor. It's a common vector here. And also here we have UR, UR, and UR. So if you just regroup this, and we can write this in this form, because if you just take this U1 out, what do we have here? C1 times A1, 1, that's the first number here, plus C2 times A21, that's the second one, and CSAS1, that is the coefficient of the last row. Plus, in similar way, how about U2? U2 also here, actually U2 we have here, we have U2 here, we have U2 here. If you just take this out, what we have here, C1 times A12, that is C1 times A12, C2 times A22, C2 times A22, plus CS times A2R. And also in similar way, and UR is a common factor. So here we have C1 times A1R, C2 times A2R, and the CS times ASR, right? Now what we have here, again, we just have a linear combination of this U1, U2, UR, right? And we know that actually, since this B is a basis, because we're supposed it's a basis for the subspace S, that means that these vectors are linearly independent. And the only way actually their linear combination is equal to 0 vector means that all of these coefficients, right, this one and plus this one, and actually this one, not plus, each coefficient must be equal to 0. That means that if I just form the system, then these are the coefficients, because since we know that they are linearly independent, and these coefficients, right, this is the coefficient of U1, The second row is the coefficient of U2, that's equal to 0. And the last one, that's the coefficient of UR, that's equal to 0. And what we have here, actually here we have a homogeneous system of how many equations? Here we have R equations, right? That's the first row, the second row, and the last row. So here we have homogeneous linear equation. How many equations? Here we have R linear equations, right? And here we have R equations. And here are equations, but how many variables we have here? If you just count the variables here, it's 1, 2, 3, and here we have S variables, right? This is the first variable, the second one, and third one. And here, the C1, C2, CS, they are just written in front of this A11. It doesn't matter, actually. It doesn't change the solution of the system, right? So now, since at the beginning, actually, if you remember, we suppose that R is less than S, right? R is less than S. So since R is less than S, what is R? It is the number of equations, and this S is the number of variables, right? And here we have the number of variables is greater than number of equations. That means that it's like, here we have something like this, maybe 3x plus 2y is equal to 1. We have two variables, one equation, and we know that it has infinitely many solutions. Or we have something like this. Here we have x plus y plus z is equal to 2, and let's say 2x plus y minus z is equal to 5. And here we have three variables, and we have two equations, and also we know that it has infinitely many solutions. And here we have also this case. Here we have R equations, and we have S, variables, right? And C1, C2, and CS, S variables. And this forces that actually this homogeneous system has infinitely many solutions. That means that the number that satisfies the system, actually the C1, C2, and CS, it is not unique, right? It is more than one. That means that now we have contradiction here. That means that here this C1, C2, CS, we don't have only one set that takes to the zero. We have more than one solution. One is, of course, when all the C1, C2, CS are zeros, and also it has non-trivial solution. That means that this V1 and V2 and Vs, these vectors are linearly dependent. That means that it cannot be a basis for S. In similar way, and also we can show that actually if you just interchange the roles of B and C, we can show that this R also cannot be greater than S. So that means that now we have only one option left, since we are talking about two real numbers. If R is not less than S, or it's not greater than S, that means that R must be equal to an R. Just example that, and also since also R is not greater than S, that means that then R must be equal to S. Okay, very good. Now we have these facts. Now we know that actually if you're talking about any subspace, and if we are talking about different bases of this subspace, now we know that actually always all the bases have the same number of basis vectors. Now, since all bases for a given subspace must have the same number of vectors, now we can actually give a special name to this number, which is called the dimension of subspace S. So if S is a subspace of Rm and dimension space, then the number of vectors in the basis for S is called the dimension of S, denoted by this dimension of S. Now here we have a remark. Immediately we can just think about a subspace that has only one element, that is zero. What can I say about zero? So zero vector, actually that is zero vector, divided boldface, by itself is always a subspace of Rm, right? Why? Because when we talk about this subspace, this zero, right? You're just talking about some kind of S. Let me just write here S, and it has only one element here, that is zero vector. It's not a scalar, it's a zero vector. And as you see here, for a subspace to be, for this set to be a subspace of Rn, it must satisfy those three properties, right? The three conditions. Number one is it must contain zero. It has zero. If you just pick two elements, actually we have only one element here, only zero as zero. If the sum is zero again itself, and if you just multiply the zero by any scalar, again it produces zero vector, right? It's actually, that's why it is a subspace for Rn. But, and also we know that any set containing the zero vector, right? If you just add zero vector to any set, and it becomes linearly dependent. So this zero set cannot have a basis. And we are just actually defining this, dimension of zero as zero. So dimension of this one that contains only zero vector is zero. Now another example, every standard basis for Rn has n vectors. So dimension of Rn equals n. Why? Because we know that if you just pick one basis, right, the standard basis, what are these bases? Those are E1 and E2 and E sub n. And even if you just form other bases, we know that it will have n vectors here, right? So since the standard basis, it has n vectors, so dimension of n-dimensional space is n. So that means that to span this n-dimensional space, we need n, what is it, linearly independent vectors. Okay, another example. How about this one? And also, actually, we did this example earlier in the previous videos. Now, if you're given a matrix, and here, what is it? This matrix that is 4 by 5 matrix, right? Now, to find its dimension, immediately we have to reduce this to row echelon form, but here it is reduced row echelon form, and we don't have to reduce this to reduced row echelon form if you're not solving a system here. Just here, I want to know how many pivots does it have. As you see here, it has 3 linearly independent vectors here, right? Actually, it's pivots or leading ones, let's say. It has 3. And others are dependent on this. So that means that using these 3 columns or using these 3 rows, right? And using these 3 rows, we can span the row space of this matrix. Or using these 3 columns, we can span, what is it, the column space of this matrix. So here also, the dimension of A, since it has 3 here, 3 leading ones, so the dimension of this matrix is 3. Okay. So it's just an example, but now we can give this as a theorem, but in general also it is true. The row and column spaces of a matrix A have the same dimension. We are saying that the row and column spaces of a matrix A have the same dimension. So if you're talking about let's say here we're talking about this S1 that sets, let's say this all the vectors which are produced by linear combination of the rows of A, and let's say S2, that is column space of A, and this theorem is saying that, okay, whatever it is, actually we have this equation, dimension of S1 is always equal to dimension of S2. That means dimension of row space of A is equal to dimension of column space of A. Okay, why? That means that if you are spanning, if the basis of row space of A contains n vectors and also column space of A, it must contain the same number of vectors. That's also an interesting fact. Now, how do you prove this? So actually, we'll start from the first fact. We know that we assume that let's this R. Okay, where are we now? We assume that, let's say this capital R, it is the reduced row echelon form of A. We know how to do that, right? By just applying a bunch of elementary row operations, we can reduce A to this reduced row echelon form, right? And also we know that row space of A is equal to row space of B. And actually, it says theorem 3.20, and also we proved this. Why is it so? Because row space of A and row space of B also here R is right, and here because these are row equivalents. Anyway, so by this theorem, we know the row space of A is equal to row space of B, and using this fact, now I can just write here that dimension of row space of A, right? Dimension of row space of A is equal to dimension of row space of R. And here, this actual row space of A is equal to row space of B if this A and B are row equivalent to each other. Right? That means that if by applying a bunch of elementary row operations, can we transform A into B or B into A? Right? If it is so, we know that actually they are row equivalent. If it is so, then row space of A is equal to row space of B. And particularly, and also by applying a bunch of elementary row operations, we can actually transform form A into R, because R is just reduced to echelon form of A. So that's why here dimension of row space of A, it must be equal to dimension of row space of R. And the dimension of row space of R, what is it? If you just look at the previous example, right here we have this R. This one is, what is it? It is R. That is reduced row echelon form of A, right? And so how many vectors, actually this row space or column space is spanned by how many vectors? Actually, it depends on how many leading ones we have here, right? Here we have 3 leading ones, right? And that's why dimension of this matrix is 3. So dimension of row space of R is just the number of non-zero rows of R. That means that the number of leading ones of R, right? So let's say is equal to R. Let's just denote this thing by R. Now, also we know that column space of R is not equal to column space of R. I mean, A is not equal to column space of R. And also, if you remember, you know this from the examples, because this column space of R, right, is different because at the bottom we have zeros. Using those vectors, we cannot actually produce the vectors in the columns of A. But the columns of A and R have the same dependence relationships. And also, actually, we saw this in the examples. Therefore, dimension of column space of A is equal to dimension of column space of R. Since there are R leading ones, R has R columns that are standard unit vectors. We also see the previous example 1, 0, 0, 0, 0, 1, 0, 0. These are standard unit vectors. And these are vectors are linearly independent, and the remaining columns of R are linear combination of them. So thus, dimension of column space of R is equal to R, and that means that dimension of column space of R is equal to R. R equals dimension of row space of R, A. So that means that row and column space of a matrix A have the same dimension. Okay, since it is so now, actually we can again give that special name to this. So the rank of a matrix A is the dimension of its row and or column spaces, and is denoted by the rank of A. So what is rank of A? The rank of A is just the rank of column space of A or the rank of row space of A. So since they give the same number, now we are just attaching a special name to this. That is the rank of A. Okay, so again, once again, the rank of a matrix actually simultaneously gives us information about linear dependence among the row vectors of the matrix and among its column vectors. In particular, it tells us the number of rows and columns that are linearly independent. And this number is the same in each case. Okay, so here we have another theorem, a small theorem. For any matrix A, a rank of A transpose is equal to rank of A. And proof is very simple. And let me just use maybe green. And it says that rank of A transpose is equal to rank of A. Now, if you just start from here, I need to show that this rank of A transpose is equal to this. How do you show that? This rank of A transpose. And just using the previous theorem, and what is rank of A transpose? That's just dimension of column space of A transpose or row space of A transpose, doesn't matter, right? Now, that is dimension of, and what is column space of A transpose? It's just the same as row space of A, row space of A, right? Because we know that A transpose, the columns of this A transpose are just the rows of A. And from here, and also from using the theorem, right? And it says the rank of a matrix A is the dimension of it is row and column spaces, then it's denoted by A. So here, dimension of row space of A using this definition is just, what is it? The rank of A. That is how you prove this theorem. Okay, here we have another definition, and we talk about null space. Now also actually we can just give a special name to the dimension of that null space. So the nullity of a matrix A is the dimension of its null space and is denoted by nullity of A. Again, actually, what is it? It is the number of vectors in the basis of that null space. Okay, now here we have another theorem. If A is M by N matrix, then rank of A plus nullity of A, that is always equal to N. And if you're talking about a kind of matrix that has N columns, and if it is a coefficient matrix, what we know actually about this, we know that N gives us the number of, what is it, variables, right? So now, like for example, let's say if you're talking about something like this, 1, 2, 3, 1, 2, 3, right? And if it's a coefficient matrix, this one is A, that means that here we are solving something like this system. Maybe here we have y, x1, x2, x3, right? And here we get the answer, whatever it is. So if A is M by N matrix, then rank of A plus nullity of A is always equal to N, right? And also, actually, we observe this in a lot of examples, because if you solve the system, right, here we have the variables, let's say this x, y, z, right? The rank of A means, what is it? The number of dependent variables, right? And how many independent vectors here we have? For example, here, if these two rows are linearly independent, that means that the rank of this one is 2. So that means that nullity means the number of vectors that in the basis of null space of A. Right? That means that here we will have one independent variable here. Anyway, how do you prove this? The rank of A plus nullity of A, that's equal to N. And also, actually, I'm going to use this fact to prove a bigger theorem that comes in the next slide. So let R be the reduced row echelon form of A. And suppose rank of A equals R. And again, when I just say rank of A equals R, what comes to our mind? Immediately, if we reduce this matrix A into this reduced row echelon form, this R is the number of columns, right, that contains pivots or leading ones, or simply R is the number of leading ones in the reduced row echelon form of A. Then R has R leading ones, so there are R leading variables. And we have N minus R free variables, because if you're talking about 3 variables, if 2 of them are, let's say, leading variables, and the rest must be free variables. So N minus R free variables in the solution to AX equals 0. Since dimensional null space of A equals N minus R, then we have rank of A plus nullity of A, that's equal to R plus N minus R. And if you just simplify this, we get N. So the sum is always equal to M. Okay. Find the nullity of each of the following matrices. Okay, what is the nullity? Again, sometimes if you have never read this before, it may sound a bit weird, but when you just say nullity, it's just simply, it's the dimension of null space of A, right? Now look at the first one, since the two columns of M, right? It has two columns in two different ways, we can find this, but since the number of columns is less than the number of rows, we better just use the column space of this M. So from here, it is obvious that these 2, 1, 4, 3, and 3, 5, 7, 8, these two columns are linearly independent, right? So that means that from here, I can just write here dimension of M, that is equal to, what is it? It is not dimension of, okay, where did it go? Here we have rank of M, that is equal to 2, right? And also using the previous theorem, now I can just write here, we know that the rank of M plus nullity of M, that's equal to 2. This M, because this one is M by N, this one is 4 by 2 matrix. What is our N here? N equals 2. And since the rank is equal to 2, the nullity must be equal to 0, right? So nullity of M is equal to 0. And how about this M? To do this one again first, I cannot see this actually. All of these, the vectors in the rows or columns, they are linearly dependent or independent. To do this, we have to just reduce this to a row echelon form. And if you just apply a bunch of, what is that, elementary operations, I can just simplify this. I will get, we have nothing to do with the first row, 2, 1, -2, -1. And if you just multiply -2 and add to the second row, and here we have 0, 2, and the 1, 3. And if you multiply the first row by -1 and add it to the last row, here we have 0 and what is it? 2. Okay. -1 is 2, -1 it is 6, and the -1 is 2, 2 plus 1 it is 3, and the -1 is 1, 1 plus 8 it is 9. Now, if you multiply the second row by -2, I mean -3 added to the third row, it will be 0. So here we will have something like this: 2, 1, -2, -1. Here we have 0, 2, 1, 3, 0, 0, 0, 0. Right? And we know that actually here it is 3 by 4 matrix. That means that we are talking about M by N, so our N is 4. So now we need to find the nullity. And from here, we can see that actually the first row and the second row, they are linearly independent, because the multiple of the second row, it doesn't give us the first row, never, because of this 0. So that means that, again, using the previous theorem, rank of N plus nullity of N, it should be equal to, what is it? 4. So from here, what is the rank of the matrix? Is equal to 2. And nullity, we don't know. So we're going to find this. So here we have 4. So from here, the nullity of this matrix must be equal to 2. So that means that if this matrix forms a coefficient matrix, and if you're solving a homogeneous system, that means that here we will have 2 dependent variables or leading variables, and we will have 2 independent or free variables. And just using this one. Now, again, just Collecting all of these facts, we can expand over this fundamental theorem of invertible matrices. And there's 5 of them we have already seen and proved this. If you remember that A, B, and N by N matrix, the following statements are equivalent. That means that if one of them is true, that means that all of them are true. And if one of them is false, that is not true, then none of them is true. So if A is invertible, if you suppose that, then the rest of all the facts here, they must be true. And if you remember this, AX equals B, that equation has a unique solution for every B in Rn, and AX equals 0 has only the trivial solution. And reduced row echelon form of A is identity matrix, and A is a product of elementary matrices. So now we can add more. Then, since again we are talking about N by N matrix, right? The rank of A must be equal to N. And using the last theorem, we know that the rank of A plus nullity of A, it should be equal to N. Since rank of A is equal to N, then nullity of A, it must be equal to 0. And column vectors of A are linearly independent, and the column vectors of A span Rn, because column vectors of A are linearly independent. Why? Because its rank is N. It means that it has N leading ones. That means that each column is a standard unit vector. So all columns are linearly independent. And since they are standard unit vectors and they span Rn, and column vectors of A form a basis for Rn. Why? Because they span Rn and they are all linearly independent. That's why they form a basis for Rn. And the row vectors of A are linearly independent, and the row vectors of A span Rn. The row vectors of A form a basis for Rn. Okay, we have 2 important theorems. I will do them in the next video. Let's have some break now. We'll continue after 10 minutes.